Hi everyone. Um, this is video lectures I'm making. Um, I heard from some of the students that Professor Shudi hadn't covered the lecture 20, so this time I'm making these makeup lectures about lecture 20. So I'm sorry, I'm a little bit sick. I caught a very bad cold. So forgive me during this lecture if I sneeze, I cough, or say something wrong. Okay, thank you so much. So before we started this lecture, a couple of things to announce. The first thing is that remember the final exam date. Okay, it's Tuesday, December 12th. 12:30 to 2:30. And don't forget to take the course evaluation survey and send me an email for extra credit. It's 3 point, so don't forget. And so for the lecture 20, what we are gonna focus is on link layer, the end of the link layer, in which we will discuss the local area network. So in local area network, the key part is switches, and we will learn how the switches work and a series of important concepts. And also the VLAN, which basically is virtual local area networks, very commonly used nowadays in internet. Okay. So talking about the Ethernet switch is very important devices you see a lot. So at your home, you may have a switch. So in student network, you may also have a switch. So the basic functions of switch is to use it to store forward Ethernet frames, which means it works in data link layer, right? So the basic functions, or what the switch does, is that it examine the incoming frame's MAC address and selectively forward it to the destination outgoing link to the correct position, outgoing port, and is totally transparent to the host, which means that the hosts themselves are totally unaware of the presence of switches. They are totally invisible to the host, and is plug and play. Okay, which means that you don't have to manually configure it to work as you want. You just plug your host in the switch and it works. Because of the mechanisms, a mechanism called self-learning. We will have more discussions about this technology, self-learning. So in switch, the basic ideas is that each hosts are all the hosts are connected to the switches with their dedicated links. So usually you can on a switch you can see many ports. So each port will have a dedicated link to connect it to a host, and the switches will buffer these packets. And the switch work in a store and a forwarding paradigm, which means that whatever packet you send out from a host, it will be stored and in the port by the switches, and then forwarded to the right destination. It's different from the hub or some other devices in the sense that each of these spokes in this graph is individual collision domain. Okay, and whatever packet you send out is stored and forwarded by switch, which means essentially there's no collision because of store forwarding. The reasons of collisions in the old days is because everybody tried to send simultaneously. But in switch, no problem because of the store and forwarding paradigm, because of the buffer you used in the switch. Okay, they can wait, so no collisions. So in the sense that each of these book is an individual collision domain, but not all of them, right? All of them is in a broadcast domain, but not in an individual collision domain, because the packet sent out by all these ports and these hosts, they do not collide. So they are not one single collision domain. Remember the difference between the broadcast domain and the collision domain. So because of the store and forwarding paradigm, so supposedly if you are sending one packet from A to A prime, and you want to send from B to P prime at the same time, no problem because of store and forwarding paradigm by switch. Remember, it's a very important characteristics of switch. Sorry. So you may ask the questions: how would the switch know where to forward the frame? Right. So for example, if A want to send it to A prime, how would it be able to know that A prime is reachable from port 4 and B prime is reachable from port 5 without sending to the wrong port? Okay. So the answer is that each switch actually it maintains a switch table. So the switch table is similar to the routing table. So the differences is just, the switch table is only for this local usage. The routing table is for either local domain routing or interdomain routing involving a lot of routers and the different subnets. But for switch, it's work only for the same subnet. Okay, so this table only work for this hosts in the same subnet and in the same broadcast domain. So the switch table consists of a series of information, useful information, which include MAC address, interfaces you can reach to a specific port, and then timestamps. So you may ask the question, okay, we know that routing table can be created for routing, but how would a forwarding table, switch forwarding table is created for this switch? Is that something like a routing table, or the process is similar? That's a big question mark. So the answer is that the switch will build this switch table by themselves by using a mechanism called self-learning. So which means that by using plug and play and start from scratch, the switch will be able to build such a table step by step, and self-learning is to learn which port is reachable, which host is reachable from which port gradually. So the idea is when a frame received by the switch, it will learn the location of the sender. Okay, the incoming, for example, incoming port, whenever it receives a segment of frames, it will look into the frames and see where does it come from. For example, if it is come from port 1, then it will be recorded, and a new entry of the forwarding table will be created. Okay. Similarly, every time it receives a packet, it will see if there is an entry. If not, then a new entry will be created for each of these hosts until all the hosts are kind of having one entries in the switch table. So, for example, at the beginning, supposedly the switch table is empty, and if the host A is sending some frames to host B, host A prime. Okay, so these frames will arrive at the switch. And the switch will look into this and know exactly where it is come from. It knows it's come from port 1. So an entry for MAC addresses of host A is created and is marked as interfaces 1, which means come from interfaces 1. TTL is 16, right? So similarly, every time when it received, it will do similar things and add entries to this switch table until every node, every host has an entry in the switch table. Then the self-learning process is finished. Okay, so because the plug and play and the transparency of the switching table initially is empty. You don't need any previous messages or previous configurations to make it work. So whenever the switch receives some frame, it needs to do frame filtering or forwarding before it can decide the right actions for that frame. Okay, so this is the algorithm used by the switch to do the work. So whenever a new frame is received by a switch, it will do this 1, 2, 3. First things will record incoming link, the MAC address of the sending host, and it will index the switching table by MAC address destination address. So supposedly, it will look into the switch table and find out that the existing entry for the destination MAC address. Well, it means that previously it has sent out something, right? Then it means that you do not have to recreate this entry. So what you do is basically you look into the destinations on the segment from which frame arrived. So if it's from the same port or same segment as so the destination, you look into the table, if the destination is the same from the where the packet from, then it means that you do not need to forward it to yourself, right? You are supposed to send out to someone else. You don't need to. So in this case, you don't need to send it to yourself. So in this case, you just drop the frame. If not a destination address is not from the same segment you sent, then you forwarded the frames to the interfaces indicated by the entry, basically the other port. You forwarded to the other port, right? That makes sense. So if there's no entry found in the destinations, you cannot see where to forward this frame to. Then so what we will do is, in this case, is to do flooding. Basically, you send to all the interfaces of the switch connected to broadcasting. Right? So it's quite simple. Let's see this example. It shows the self-learning process and how the switch forwarding table is built. So in this example, again, we have 6 hosts, right? And 6 ports. And again, you have host A try to send some frames to host A prime. The source MAC address and destination MAC addresses is kind of contained in this frame. And you send it out, and it is received by a switch. And it's created an entry for you, right, for A. But unfortunately, you didn't see an entry for A prime because it's totally empty at the beginning, right? So you don't know where to forward these frames to. You don't know that A prime is connected to port 4. So what you can do is to do flooding. So basically you send these frames, the duplicate frames, to all the other 5 hosts by flooding. So eventually A prime will know that, okay, this is for A prime. So it will reply and send response frames to the switch, and it will be recorded, right? It will be recorded into the switch table because this is the first time prime send out something to the switch. So this new entry will be created, meaning that the hosts A primes can be reached from interfaces 4. Okay, so the next times, when it got this response, the switch will realize right away that that frame should be sent to A prime in the future. If the destination MAC address is containing A prime, right? So after that, the switches will forward the response frames back to A because the switch already knows that A is reachable by interfaces 1, right? Because this entry is already created. So the response frames will be able to arrive at A's directory without doing flooding. Okay. So the response or back frames will be selectively sent out on just one link. So now you may ask the question, okay, so one single switch's case is fine, right? So it's quite simple. You just do self-learning and build the forwarding table from scratch, and you get it done. But in reality, there could be many different switches which are connected together. It may be a hierarchical structure showing like this. You may have this switch, this host, this switch, this host, this switch to this host. So you may ask the questions: if host A want to send something to host G, how does the S1 and S3 to be configured? So the forwarding table of this S1 and S3 and S4 can be created for these purposes, for them to work together. So this process is called self-learning again. Okay, even though the network structure is a little bit complex than the previous example, but it will still work out by self-learning by doing this flooding. So this is a simple exercise you can do to, for example, to show the four switch tables and packet forwarding in S1, S2, S3, S4. Okay, that's the exercise you can do offline. So talking about the switch, a very typical institutional network, usually you will see a lot of switches. So a typical institutional network like AMSO's, pretty much we will have one outgoing router, and inside you may have many routers. But if it's a small enterprise or institute, it may have only one outgoing router, but inside they may be connected by many switches. And the switches may connect to the servers like mail server, web servers, and then the other hosts connected. It's a very typical institution network structure. So switch is very commonly used. So when you see routers and switches, you may ask the questions why they are all needed, or what are the differences between them. So we know that first, both router and switches are based on store and forwarding paradigm. But the routers is network layer devices, which means that the store and the forwarding is based on the IP datagram, right? Excuse me. So, but the switch is like link layer devices. It only examines the link layer headers, not the IP header, right? So, for example, if you have a packet, if you go through a router, right, the datagram. So for the switch, it will only look into the link layer. It want to look into the IP address, transport layer applications. It does not do that. But for the router, if it is a regular router, then it will look into the IP datagram, which means the IP address will be looked into. And to do routing, for example, right, to check the next hop, and then until to arrive at the host. Host is all the 7 layers will be read. And both of routers and switches have forwarding table. For the forwarding tables of switches, we have learned that they are built out by self-learning, by flooding. All right, it's quite simple and straightforward process. But for routers, the routing table, we also discussed the routing table, how they are built, right? Already in the last chapter in the network lab. Okay, we will not repeat that, but they have different process of building these tables. And for LANs, a very important concept you have to be very careful is that a local area network actually is a subnet. Okay, a subnet or a LAN usually is a broadcast domain, which means that when you send some packet, that's the range that you can do broadcasting. So whatever you send out, these clients will be able to see each other. They can send out directory. They can do broadcast directory. They can send out, see each other directory, right? By doing broadcast, but not across different LAN. For communications across different LAN, you need a router. Okay, so each LAN actually is a broadcast domain, not a collision domain. Okay, remember the collision domain and the broadcast domain. Collision domain is totally different concept. It's about how these devices can, if they compete the physical network link, then they may collide with each other, and they are kind of in the same colliding domain, like in your Wi-Fi access point range, right? Or in the Ethernet, in the same Ethernet domain, right? But for broadcast domain is wider. It's like for broadcast, MAC address broadcast, not physical access or MAC access. So for LAN, it's a single broadcast domain or subnet. There is no routing is needed in the same subnet. But between different subnets, you need a route and you need to do routing. Okay, that's a very important concept you have to be careful with. So after the LANs, we have a VLAN. So the VLAN concept is very important and useful. So in this, as shown in this graph, you can see that inside the institution network, you may have many departments like computer science department, electrical engineering department, and other department. So you may consider the case or scenario that if a specific computer science users move offices to EE and want to connect it to CS switches. So if this is the case, because of the move, if you want to make it happen, there have to be a single broadcast domain, which means that all the layer 2 broadcast traffic must cross the entire line. Actually, this is a clumsy design because there's a couple of significant issues like security, privacy, efficiency issues, right? For example, you definitely, inside the computer science network, you definitely do not want to see the broadcast information from the other educations or other schools broadcast, right? You don't need that information. You just want to see your own domains in local area network or LAM's broadcast domain. So we need some kind of traffic isolation. So that can be handled by VLAN. Instead of building a huge LANs, with many hosts, we can build individual, logically isolated virtual LAN. So actually, the VLANs is a very useful concept because it make the LAN structures in location independent, which means that you can physically move to the other location, but logically you can belong to somewhere else. Okay, for example, marketing area LANs you can be all of the buildings, right? They do not have to be fixed in the same places. And you can move, you can change allocation of the LANs, and you can dynamically arrange and organize this VLAN. And keep all the traffic in the same organizations on the same LAN. You do not run across this for protection, right? So privacy and security excuse me, will be a big plus. So as a matter of fact, those are principle. Switch usually is cheap. The route usually is more expensive. Okay, because switch is fast. So usually do not do VLAN over very expensive WAN links because of the broadcast traffic calculated variable from WAN bandwidth. Okay. Also bad security, as I mentioned. So how the VLAN would work? So basically the idea is the virtual local area network is that you can divide the switches port, you can group them into different virtual categories and define multiple virtual LANs of a single physical LAN infrastructure, which means that essentially you buy one single device, but you do not have to use it as one single LAN. You can divide them into any individual group small VLANs. For example, in these cases, we have two groups of ports. That the blue ports is assigned to electrical engineering. The yellow groups is assigned to computer science, and they perform just like two physical LAN or physical switch. Okay, it's very convenient, right? So when you buy something, you can configure it dynamically. It works just like many LAN. So that's a good thing. So you can do traffic isolation by use this port-based LAN. So for example, if you assign 1 to 8, to electrical engineering, then the traffic will only be limited in this among these 8 ports. Similarly for these ports, right? The traffics are isolated; they cannot see each other's frames. And if you want to talk to each other between these ports and these groups and these groups, then you may have to involve routers or routing functionalities. Okay. So in a lot of cases, in the switches, the route actually this functions is integrated. This routing function is integrated, so you don't have to buy individual routers to do these functions. Okay, and you can dynamically change the membership of these ports. For example, this port you can change it to computer science yellow ones. No problem. You can randomly assign one port to any organizations. No problem. So what if you have many switches and the VLANs, are they able to run across multiple switches, physical switches? For example, on these switches, physical switches, you have 2 groups, right? And you buy another switches, and it has some ports. You have some switches connected to you assign some of the port to into electrical engineering and some ports to computer science. So actually it can work. The idea is you needed to use a chunk port between the two physical devices and to bring them together so they will be working just like big switches with two group of nodes or ports. Okay, so to make this happen, and conditions is that you must carry some additional VLAN ID information to make sure the frames going through these links can be grouped to the right port, right? To the right group. So, which means you have to define some additional mechanism to make this thing happen. So actually, it's L2.1Q protocols define the additional header fields containing the VLAN tags for these purposes, so that the channel port that are connecting multiple physical VLANs allow you to form larger VLANs. Okay, so extend the size of these VLANs by using chunk port. So this VLAN ID information actually is in L2.1Q frames. What you needed to do on top of the original L2.1 frames is that you need to add tag or VLAN information, which consists of tag protocol ID identify 2 bytes and tag control information ID. So in total, you needed to add 4 additional bytes VLAN tags for L2.11Q 1Q frames to make it work. To work with its VLAN channels. So the next topic is this data center networking. We kind of skip the MPLS part. For data center, nowadays it's very common to see everywhere. So every big company like Google, Facebook, Microsoft, they all have data centers. Usually they can consist of many thousands of hosts. They are closely coupled in close proximity to do, for example, e-business, for cloud computing, client servers like YouTube, Akamai, Apple, right? A lot of different companies to do these content delivery services, and also for search engines and data mining. Almost nowadays, all the applications are deployed in the data center. So the data center network is very important. And also, there are a couple of challenges to handle these data center networks. So the first challenge is that there are so many applications running and running in the data centers, and each application may serve massive numbers of clients simultaneously, right? And it's very important for you to manage the load balancing. To manage the load balancing, issues and avoid data bottlenecks, right? So usually this is a very typical data center network. So supposedly this is a border router, and this is below that you have many access routers and there's many tier 1 switches, tier 2 switches, and top of the rack switches, and many servers. So you can see the servers are at the end of this hierarchy. So for the load balancing, actually what it does is application layer routing, which means that whenever you receive a application request, you you goes to the load balancer first, and the load balancer will assign you to a specific rack. And if the rack is too high, then it may run and coordinate with different racks machines, and they can distribute the amount of the work and computation, for example, tasks, and get it done and then respond it to the outside world. So you can see that in data center network, you need it to happen very fast, which means that you need to provide a very rich interconnections among the switches and racks, because they are handling so many requests and services, and this, you need to make sure that if one of the link or one route or one switch is down, you can still get it connected. They will not break your services, right? So very rich interconnections you can see between the tier 1 and tier 2 switches. So they are kind of fully meshed. So in the meantime, it can increase throughput because of multiple paths, right? The throughput can be increased. And also reliability can be increased because of redundancy. One goes down, doesn't matter, still can work, right? That's a good thing. Okay, so this is basically the lecture 20s we have discussed. So hopefully, so the next lecture actually I made it early yesterday, which is about mobile and wireless connections, mobile and wireless networking. Lecture 21st. I also uploaded it to the YouTube, so please find these two lectures and watch them and ask me any questions if you have. Okay, thank you.